go. All right. So we left off last class. We actually stopped right here. And I said, well, on Friday, we'll tackle these questions. Okay. But just to rehash a couple of reactions, I want to back up a little bit. Okay. Because there's some reactions that we did cover pretty quickly. And the reactions of alcohol. So we saw that a tertiary alcohol can undergo an SN1 with hydrogen bromide to give you a tertiary alkyl bromide. We said that a primary or secondary alcohol can undergo an SN2 with HBr to give you a primary or secondary alkyl bromide. Then we said if you have, if you want to make an alkyl chloride, you have to use zinc chloride to get that to go. And there's a reason for that. It's HCl isn't as strong as an acid as HBr. I told you don't have to know this mechanism. You can even see my scribble, or is it right here? I said I will not ask you this mechanism. You just need to know that zinc chloride is the Lewis acid in there. Then we talked a little bit more about tosylates, right? This is something that we learned back in Organic Chemistry 1, but we said we can do an SN2 with a tosylate, right? And then these are two new reactions that we covered last class, okay? So I went over SOCl2, which is thionyl chloride, which converts a primary or secondary alcohol to a primary or secondary alkyl chloride. So that's thionyl chloride, that's this guy here. I went over the Lewis structure, and it's in pyridine, and you should know that pyridine is this compound here. And then we said phosphorus tribromide, that takes a primary or secondary alcohol and converts it to an alkyl bromide. So I showed you the mechanisms, which both involve converting the poor leaving group into a good leaving group, and then an SN2. But I told you I will not ask either of those mechanisms. However, what you do need to know, and this is important, okay, trust me, this is very, very important, is that when you do these mechanisms, remember, if you convert a bad leaving group into a good leaving group, and then you do an SN2, remember the SN2, if there's a stereocenter, it proceeds with inversion of configuration, okay, because chirality is important in organic chemistry. So we covered both of those. We covered dehydration, and we talked about Zaitsev and Hoffman, and how if you just take an alcohol and heat it up in concentrated sulfuric acid, you're going to get a mixture of the Zaitsev and the Hoffman. The Zaitsev is going to predominate, and if you only wanted to get one of these radioisomers, you would have to go through forming the tosylate and then treating it with a base. All right, so with that in mind, let's see if we can find a way to do these transformations. So in the first one, we're taking a secondary alcohol. So we have a secondary alcohol, and we're converting it to a secondary alkyl halide. But you notice that this is proceeding with inversion of configuration. So based off of that, there is a reagent that we could use that is just one step. Could anybody tell me what that reagent is? And it's not a trick question. It's one I just mentioned a few minutes ago. What's a reagent that would turn that hydroxyl into a good leaving group, and then we do an SN2 to form a secondary alkyl bromide? Anyway, thanks, Mustafa. Exactly. It's phosphorus tribromide, isn't it, right? PBr3. Exactly. So PBr3 is all we need, okay? Now, if you're saying, I could have done this using the skills that I learned in Chapter 7, you're absolutely right, okay? There is another way, is we could also do this. We could first convert it into the tosylate using tosyl chloride and pyridine, okay? That would convert this to the tosylate, okay? So once you convert that to the tosylate, all you have to do is displace it with a bromide ion, an SN2 fashion. And so where would you get a bromide ion? You would get it from the sodium bromide salt. So that is the other option. Okay, so we get two possibilities here. All right, for the next one, we're taking a tertiary alcohol, and we want to convert it into a tertiary alkyl halide. So tertiary alcohol, we want to convert that to a tertiary alkyl halide. Now again, this is something that we would have seen a little bit of in Organic Chemistry 1. Could anybody provide a one-step reagent for this one? Just a one-step reagent for this one, sorry. So it's not going to be PBr3. So PBr3 won't work in this case, okay? I'll tell you why, okay? So we'll put here PBr3, we'll cross it out, okay? The reason why PBr3 doesn't work, you go back here, is because it says that PBr3 only works with primary and secondary alcohols. It doesn't work with tertiary. Okay, let's go back in our slides again, okay? If we want to take a tertiary alcohol, tertiary, and we want to convert it into a tertiary alkyl halide. What do we need? We just need HBr as our reagent, okay? So let's go back to the problem here, okay? And the reagent that we need in this case is HBr, okay? This is just an SN1 mechanism, all right? So the next one, we're taking a secondary alcohol and we're converting it into a secondary alkyl chloride. So in this case, there's a couple of possibilities. Does anybody have an idea about this one? Excuse me. Anybody have an idea about this one? Remember, it's not a bromide this time, it's a chloride and it's secondary. Okay, so we don't need zinc chloride in this case, okay? Yes, SOCl2, exactly. That's going to be the reagent that we would use in this case, okay? So we would use thionyl chloride and pyridine is the best choice, I would say. SOCl2 and pyridine. Pyridine, okay? There is another option, okay? We could do it the long way. We could treat it with tosyl chloride and pyridine to form the tosylate, and then we could displace it with sodium chloride, right? Chloride is a weak base, but it's a very good nucleophile. Okay, and so for the last one, we want to take a secondary alcohol and convert it into a secondary alkyl halide. We're getting inversion of configuration. It's actually just a repeat of the first one. And so the best option there would be to use phosphorus tribromide, like that. All right, there you go. So down the hatch. All right, let's try this one here. So now we have a tertiary alcohol, and we're treating it with concentrated sulfuric acid. So remember, if it's concentrated sulfuric acid, that means there's very little water in it, and we're heating it up, so that means we're going to drive water out of it, right? Think about when your body heats up. What do you lose? You lose water as sweat. So it's the same thing in organic chemistry. When you heat something up, we put a little negative for losing, you lose H2O. So if we lose H2O from this molecule, we're going to end up with an alkene. So what are the two possibilities? Well, I could form the Zaitsev alkene and I could form the Hoffman alkene. Okay, I got two possibilities. So I'm going to draw both of them. Okay, so I'll draw this alkene as one possibility, and I'm going to draw the other possibility. Could anybody tell me, is it the red one or the blue one that is the Zaitsev product? The Zaitsev product, based off of what we covered in Organic Chemistry 1. Thanks, Mustafa. Absolutely. This is the Zaitsev product. Why? Because it's the more substituted of the two, right? And the one that's less substituted is going to be the Hoffman product. Now that we have that, could anybody tell me which one is going to be the major product? Which one would be the major product based on, it's really just based off of thermodynamics. Yeah, it's going to be the red one, right? The Zaitsev product is going to be Zaitsev and major product. All right. I would also say that you should be able to draw a mechanism for this reaction, right? You should be able to draw the proton transfer to convert this into a good leaving group. Then it's tertiary, so you're going to have laws of leaving group, form a carbocation, then you get a proton transfer to give you the final product. So I would say you should be able to draw this mechanism as well. All right. So with that in mind, it says here oxidation of alcohols. So this is something that we've covered already. So I think this is actually in the wrong place. So I'll just move on to this slide here. Okay, so let's get into oxidation. So last class, we talked about how to evaluate an oxidation number. So if we review that, let me get my red pen. If we take a look at this compound, right, if I redraw it here, so we have a bond between carbon and oxygen, then we have a bond here to a methyl group, another bond to a methyl group, and then a bond to a proton. So remember, we break these bonds heterolytically. So if we break the one between carbon and oxygen, oxygen takes the protons. The electrons. If I break the ones between the carbons, then each one gets one because they have the same electronegativity. And then you know that carbon is more electronegative than hydrogen. And so the carbon is surrounded by 4 electrons. So our oxidation state would be 4 valence electrons minus 4 dots minus 0.6, which gives you 0. So the oxidation state of this carbon is 0. Okay, so if it's oxidation is losing. So that means that this carbon should have a higher oxidation state. So if I redraw the molecule like this, I'll be quick about it this time. So if I erase everything, okay, so the carbons are going to split the electrons. Everybody gets 1, and then the oxygen's going to get all of them. So now the carbon is surrounded by 2. So we have 4 minus 2 dots and 0.6, which gives us +2. So we go from 0 to +2. So is that oxidation? Sure, absolutely it is when we go from 0 to +2. And if you're thinking, what does that have to do with oil rig? What I would have learned in general chemistry, oxidation is losing. Losing what? Losing electrons. If you lose electrons, which are negative, you become more positive. So we clearly see that this is oxidation. Now, an even quicker way of looking at it is that you notice that you lose 2 hydrogens. Did you notice that both of these hydrogens are not present in this molecule? They're gone, okay? If you look at the formula of this compound, we have 1, 2, 3 carbons. We have a total of 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 1 oxygen. Whereas here we have C3H6O. So we lost 2 hydrogens. So you can also think of oxidation as losing hydrogens, or another way, so a third way to think about it is that we're gaining bonds to oxygen, right? Here we have 1 bond to oxygen, but now we have 2. So losing hydrogens is oxidation, and gaining bonds to oxygen is also oxidation. Now, if we were to do the converse process, if we were to take that ketone and convert it to an alcohol, we saw last class that this would be reduction. You could do it with sodium borohydride or lithium aluminum hydride. So now we've covered oxidation and reduction in terms of the mechanics of it, but we haven't looked at any conditions that allow us to oxidize an alcohol to some kind of carbonyl compound. So let's go through that. All right. So let's start with the oxidation of a primary alcohol, right? The first thing you need to know is the difference between a primary and a secondary alcohol, right? If you remember, if you look at the carbon that is directly attached to the oxygen, if it has 1 R group on it, it's primary. If it has 2 R groups on it, it's secondary. So when we take a primary alcohol and we oxidize it, this little letter O in square brackets, this is organic chemistry speak for, it just means oxidation, okay? It could be any number of conditions, but it just means an oxidation. So if we oxidize that, first it gets oxidized to an aldehyde, right? We lose 2 protons, and we gain a bond to oxygen. So once it's oxidized to an aldehyde, the aldehyde can be oxidized even further. How do you know this is oxidation going from the aldehyde to the carboxylic acid? Because here we had no oxygen and now we have one. So gaining oxygen, like I said, is oxidation. So again, to review, when we go from the primary alcohol to the aldehyde, that is oxidation. Why? We're losing hydrogens. We're gaining bonds to oxygen. When we go from the aldehyde to the carboxylic acid, that is also oxidation because we're gaining bonds to oxygen. Now, if you're wondering, well, hold on, Mr. Dion, I thought you had to calculate the oxidation number of the carbon every time. You can. You can do that if you want to, but I'm saying it's not necessary, okay? As long as you understand that losing hydrogens and gaining oxygen is oxidation, okay? So a primary alcohol will go to an aldehyde first and then a carboxylic acid second. And what we're going to see in a few minutes is that there are conditions that will take you directly to the carboxylic acid, and there are also conditions where you can stop at the aldehyde. Now, if you have a secondary alcohol, that can be oxidized to a ketone. You notice that a ketone has no hydrogens on the carbonyl carbon. Well, if you're astute, and I know you all are, you probably realize that unless the carbon attached to the oxygen has a hydrogen on it, oxidation can't occur. So generally speaking, ketones don't oxidize any further. However, in chapter 19, so you don't have to worry about it for quite a while, in chapter 19, we will talk about an oxidation of a ketone, but for this chapter, it's not pertinent whatsoever. Now, students love rules that there's no exceptions to. You guys want a rule where there's no exception in this universe, and that is a tertiary alcohol. It says here, if you try to oxidize a tertiary alcohol, nothing happens. Why? Because nothing happens, okay? And if you're wondering, is there an exception? Maybe there's some really strong oxidizing agent. Nope, it can never happen. The reason why is because the carbon, the alpha carbon, has no protons attached to it. You have to have a proton attached to the alpha carbon, so this is the alpha carbon, in order for there to be an oxidation. So there are no exceptions to this rule. All right, so with that in mind, let's talk about what are the oxidizing agents. I think we learned maybe about 5 of them. There's about 5, maybe 6 different oxidizing agents that we learned in this class. All right, so let's get started. Let's take our journey through our oxidizing agents. It says there are a large number of oxidizing agents out there that can be used to oxidize an alcohol. But the most common one is chromic acid. Okay, do you guys remember if I was to draw or to give you this formula, H2SO4, aqueous, could anybody name that acid? What's the name of that acid? H2S.
Is it sulfuric acid?
Sulfuric acid, right? So we have sulfuric acid. Thank you, sulfuric acid. And so now if we just change the sulfur for a chromium, we get H2CrO4. And we call that chromic acid. Chromic acid. So if you know the Lewis structure of sulfuric acid, all you have to do is replace the sulfur with a chromium, and there you go, chromic acid. The thing about chromic acid, though, just give me 1 second here. The thing about chromic acid, though, is that you can't just buy a bottle of chromic acid. Okay, there's no such thing. It doesn't exist. Chromic acid has to be formed in situ, which is Latin for in place. You have to make it in a flask and then use it. Okay, so there's 2 ways you can make chromic acid. Sometimes people will call chromic acid, they'll call it the Jones reagent. The Jones reagent. I'll just put reagent. Okay, our textbook doesn't use that. I don't know why I put apostrophe in there. The Jones, come on, you. The Jones reagent. Okay, our textbook doesn't call it that, but if you do a Google search, sometimes people call it that. So there's sort of 2 ways to make chromic acid, all right, and they involve quite a few moving parts. The first one is to mix chromium trioxide, aqueous acid, and acetone. So if you were to put that in a reaction, you'd say CrO3, H3O plus, and acetone. Okay, that's one way of making chromic acid. Another way is to use sodium dichromate and sulfuric acid and water. So you'd write that as sodium dichromate, Cr2O7, kind of running out of space here, sulfuric acid, and water. Okay, both of these do the exact same thing. Okay, they just make chromic acid. The chromic acid is a very, very strong oxidizing agent. So I'm going to circle it and say very, very powerful. It is a very strong oxidizing agent. So with that in mind, I told you that you don't need to know the mechanism of the oxidation reactions, okay? But the more you understand it, probably the easier the class becomes. So how does chromic acid, how does it oxidize an alcohol? Well, it's a 2-stage process. The first stage is that the chromic acid reacts with the alcohol to form what we call a chromate ester, okay? And then once you form the chromate ester, you see that there's a series of curved arrows that occur here, and you end up doing a proton transfer, and then you form the double bond to form the carbonyl, okay? Again, I will not ask this mechanism. Okay, you need to know the reaction, but you don't have to be able to draw this mechanism of the oxidation with chromic acid. Now, like I told you, chromic acid is really, really powerful. It is very strong. And so if you take a primary alcohol and you treat it with chromic acid, what it's going to do is it's going to go all the way into the carboxylic acid. So if we put here chromic acid, let me just write down one of the sets of conditions. So I'll put sodium dichromate, sulfuric acid, and water, like that. Okay, so if you treat a primary alcohol with a carboxylic, with chromic acid, it goes right to a carboxylic acid. So then the question becomes, well, is there a way for me to go from the primary alcohol to the aldehyde directly and stop there? And the answer is yes. Okay, so you have to use a much milder oxidizing agent, and it's called PCC, which stands for pyridinium chlorochromate. Okay, PCC, right here. You can see it's this chromium salt. You've got a cation, you've got an anion. Don't worry about drawing the structure of that compound. Usually my students just remember the acronym PCC. They say it's a weak oxidizer. And what does it do? It allows you to convert a primary alcohol to an aldehyde, and it stops there, okay? So we'll say here, no more oxidation, okay? So it doesn't oxidize it to a carboxylic acid. PCC is a red solid. It's a really great compound. It's very easy to mass on a balance. So you throw it in your reaction flask, it spits out the aldehyde, or produces the aldehyde, I should say. Then you have to collect it. But there you go. So PCC, weaker oxidizing agent. There's just one problem with both of these, okay? I'm not going to ask you what it is because you'd probably never guess unless I told you, okay? And the problem with both of these reagents is this little element here. It's chromium, okay? So there's chromium in periodinium chlorochromate, PCC. There's chromium in chromium trioxide. There's chromium in sodium dichromate, okay? There's chromium in all these. And if you're a student, which I know you all are, all of these, what do they have in common? They all have chromium with a +6 charge, okay? But anyhow, or +6 oxidation state is what I should have said. But anyhow, that's neither here nor there. But the thing is that chromium is bad for the environment, okay? So the chromium ends up in the waste, and I don't know about you, but I don't enjoy polluting, okay? So if I can avoid using chromium, I would, okay? Because it is nasty for the environment. So what are your possibilities? Well, before we get into them, I want to remind you that if you have a secondary alcohol, remember that a secondary alcohol only has one proton on the alpha carbon. So whether you treat it with a strong oxidizer like chromic acid or PCC, or a weaker oxidizing agent like PCC, it's going to stop at the ketone. It's not going to go any further, right? Because I told you that this cannot be oxidized any further. It stops there. So if you have a secondary alcohol and you want to oxidize it, the world's your oyster. You just pick whatever you want and you're going to get a ketone. Whereas if it's a primary alcohol, you have to be more judicious. If you want the aldehyde, you use PCC. If you want the carboxylic acid, you use chromic acid. So again, chromium, I love it. I love the word horrible. Okay, chromium reagents are toxic and horrible for the environment. So you can imagine that lots of chemists are interested in finding cleaner ways to do oxidations, ways that are cleaner for the environment. And we're going to cover at least two of them in this class. Okay, one of them is called the Swern oxidation. So I'll just list them here. We're going to learn Swern oxidation, and then we learn another one called the Des-Martin periodinane. It's so long we use an acronym, the DMP, okay? So let's start with the Swern. And you do not have to know this mechanism. I'll even write here, will not ask mechanism. That's shown here. Okay, but the Swern oxidation is a mixture, or it's a combination of two steps. So I'll write them down here for you since they're not really on the slide. Step one is going to be DMSO, and something called oxalyl chloride. Don't worry, I'll go over this in more detail. And then the second step is going to be it's going to be triethylamine, so ET3N. Okay, so those are the steps of the Swern. Okay, it's a two-step process. So take a look. The first reaction doesn't even involve the alcohol. It actually involves the reagent. Is that dimethyl sulfoxide, okay, reacts with the oxalyl chloride. So this compound here is the COCl, okay, 2, right? There's COCl here and there's COCl there. So that's why we use that condensed formula. So it reacts with the oxalyl chloride, and then you do a loss of leaving group, okay, and then you do a substitution, so which comprises of a nucleophilic attack and a loss of leaving group, and then you make this chlorodimethyl sulfonium ion. Okay, so this is the chlorodimethyl sulfonium ion, which is a pretty interesting ion, okay, that you see here. But this is actually, again, formed from the DMSO and the oxalyl chloride, right? You mix it together, and it essentially makes this in the first step. That is the active oxidant, okay? It's not stable, and so that's why you can't just buy a bottle of that. You're like, I'll just use that instead of DMSO and oxalyl chloride. Well, unfortunately, it doesn't work that way, okay? So now you have a really powerful electrophile, and so what's going to happen in the next step is that your alcohol is going to attack that, and then you do a series of proton transfers, and then you end up with your ketone in the end. Again, I will not ask this mechanism. Will not ask mechanism. However, A couple of things you should note about this. Number one, it's a two-step process. What was step one? Step one was dimethyl sulfoxide. Step two was oxalyl chloride. So COCl2 in brackets 2. And then the second step is going to be triethylamine. Okay. And you can see where the triethylamine comes into the play. Right here in the mechanism. However, one more thing is that it also liberates, so you end up with your oxidized compound, might be a ketone, might be an aldehyde, but you also end up with dimethyl sulfide. So DMS, this stands for dimethyl sulfide, and this compound is very stinky. Okay, it's not bad for the environment so much, but it smells terrible to the point where if you do a Swern reaction, everybody knows what you're doing. Okay, everybody will smell it and be like, "Oh, I know what you're doing, a Swern." Okay, so you can't. It's one of those things you can't hide it from your lab mates. Okay, everybody will figure it out that you're doing the Swern. But what's the advantage of these conditions over the Jones reagent, the chromium trioxide, and aqueous acid and water, for example, is that there's no chromium, right? So it is better for the environment, even though it is smelly. All right. So here's the overall process for the Swern. Like I said, step one. Okay, so let's write these down one more time. DMSO stands for dimethyl sulfoxide. COCl2, right? Because it's inside brackets. This is called oxalyl chloride. And then the last step is triethylamine. Okay, so maybe I'll write triethylamine. And it is a weak oxidizing agent like PCC. Okay, and it's going to stop at the aldehyde. Now, if you have a secondary alcohol, I'll just scribble it down here. Secondary alcohol, okay, and then you do a Swern, so I won't write out the whole thing. That's going to give you a ketone, okay, but that's the same as any other oxidizing agent. All right, so the next one is, again here, our chromium reagents are horrible for the environment. So besides the Swern, the next common oxidizing agent that we're going to learn, I think this is the last one. So let me double check. I don't want to misspeak. Yeah, it's the Des-Martin periodinane. Okay, we just shortened it to the DMP, the Des-Martin periodinane. And again, I'll put here no mechanism required. Okay, you don't have to memorize the mechanism of the Des-Martin periodinane, but it's like a Swern, and then it's weak. Okay, if you have a primary alcohol, it's going to stop at the aldehyde. It does not oxidize any further. Okay, it's not going to oxidize it to a carboxylic acid. And the same thing with the secondary alcohol, Des-Martin periodinane oxidizes to a ketone. If you're wondering, what's this thing underneath, right? This is dichloromethane, and dichloromethane is just the solvent. Okay, it's a very good solvent for the Des-Martin. Periodinane. So there we go. All right. So, and as far as the structure goes of the Des-Martin periodinane, you don't have to have that memorized either. As long as you have an idea that it's just the DMP, the Des-Martin periodinane, and then it oxidizes a primary alcohol to an aldehyde and a secondary alcohol to a ketone, you're good. All right, so it's believed to proceed through this mechanism. When you're like, I'm glad he's not making me memorize that. Yeah, it's kind of a tricky mechanism that is concerted, meaning it all happens at one time. Anyhow, so it says here, DMP oxidation, non-acidic, doesn't require high temperatures. I like it. Okay, so to review, if we go back to the Swern, okay, so as I was saying, the Swern, okay, is going to oxidize to an aldehyde, and then it can't oxidize any further, okay? It will not oxidize any further. If you have a secondary alcohol, and you do a Swern, it's going to stop at a ketone. Okay, these are weak oxidizing agents. The only thing that's going to oxidize further to a carboxylic acid is something that you use to make chromic acid. Okay, that's the only one. All right, so desmertin periodinane will also stop at the aldehyde, and of course the ketone. You don't have to memorize the condition. So, what was the drawback of the Swern? Was the odor. The drawback of the periodinane is that the desmertin periodinane is shock sensitive. So shock sensitive. Okay, so that means it can explode, I guess, if you handle it in the wrong way. So that's kind of a negative. But anyhow, I digress. Okay, so now it's asking us to predict the product for the following reaction. So we have a secondary alcohol, right? We have a secondary alcohol. We have a primary alcohol. And could anybody identify this functional group here? Functional group do we have here? Can anybody identify this functional group? The red circle. Yes, it's an aldehyde. Okay, so we have a secondary alcohol, primary alcohol, and an aldehyde. All right, and we're treating it with chromic acid. Remember, the chromic acid can come from two things, okay? H2CrO4. It can come from either a mixture of chromium trioxide, aqueous acid, and acetone. So acetone, there you go. That's one possibility. Or it can come from a mixture of sodium dichromate, sulfuric acid, and water. Okay, either one of these makes chromic acid. So what does that mean? It means that our secondary alcohol is going to be oxidized to what? The secondary alcohol is going to get oxidized to a ketone. The primary alcohol is going to be oxidized all the way to a carboxylic acid. And the aldehyde is going to be oxidized to a carboxylic acid. So now if I count the number of carbons in my chain, 1, 2, 3, 4, 5, 6, 7, 8. If I put in here, 1, 2, 3, oops. Get my black pen here. 1, 2, 3, 4, 5, 6, 7, 8, like that. So I'm going to oxidize the aldehyde to a carboxylic acid. This is going to be a ketone, and then I'm going to oxidize this to a carboxylic acid as well. There we go. So there you go. So chromic acid. The only thing that can convert a primary alcohol to a carboxylic acid is chromic acid. It's the only thing. Desmartin doesn't do it. Swern doesn't do it. Has to be chromic acid. All right. So with all that in mind, let's get some more practice here. So if we have in the first compound here, how would you describe that alcohol? Is that a primary, secondary, or tertiary alcohol? Meaning this one here in the green circle. How would you label that alcohol? Yeah, it's a secondary alcohol. So if I take a secondary alcohol, and these are the conditions for chromic acid, what kind of functional group am I going to have in my final product? A secondary alcohol will be converted into a ketone. Thanks, Mustafa. Yep, it's going to be converted into a ketone, like that. Good. The next one, we have a primary alcohol, and we're treating it with chromic acid again. So if I treat a primary alcohol with chromic acid, what functional group is it going to be converted into? Anybody? Not with chromic acid. Remember, chromic acid is strong. It's the strongest one. So if I have a primary alcohol, again, chromic acid will oxidize it all the way to a if I have a primary alcohol, Okay, primary alcohol. It's getting it oxidized all the way to a carboxylic acid. All right. So there we go. So we're going to end up with a carboxylic acid. So we have a carboxyl group here. All right. The next one, how would you, what's the name that we would give to this reaction here? It's named after somebody. I'll give you a clue. It's not the Mr. Rogers reaction. Just me being silly. Who would you name this reaction after? It's named after a very famous person. Well, famous for organic chemists, I guess. Yeah, this is a Swern oxidation. So we have a Swern oxidation. So this is a Swern. And if we're oxidizing a primary alcohol, we're going to end up with an aldehyde in this case. So we end up with an aldehyde. And then the last one, we have a primary alcohol on one side. And then we have an aldehyde over here, right? So the reagent DMP is desmartin periodinane. So the primary alcohol, what's that going to get oxidized to? The primary alcohol will form a, anybody? Aldehyde, exactly. And then what's going to happen to the aldehyde? What will happen to the aldehyde on the other side? Buddy? Aldehyde on the right-hand side will get converted into nothing. Exactly. Thanks, Anastasia. Nothing, right? It doesn't get oxidized any further. There we go. So that covers oxidation of alcohols. Don't worry about section 12.11. I know that a lot of you are interested in biology and biochemistry, so if you want to read the section on NADH, you can do that. I'm sure you've learned about NADH in your biology classes, so you can look at its structure in more detail and talk about the conversion between NADH and NAD+, so the reduced and the oxidized form. I'm not going to go over that with you and how it is employed in the citric acid cycle. But yeah, so let's see, oxidation of phenol. I'm not really that concerned with that, but I'll just show you one thing kind of quickly, is that if you take a look at phenol, and you should all know what the structure of phenol is by now, this compound, you've seen it many, many times. Okay, if you look at the carbon attached to the oxygen in phenol, it's got 1, 2, 3 bonds to carbon, so you might think it's impossible to oxidize like a tertiary alcohol. It's not really true, or it's not actually true. It turns out that you can oxidize phenol, and if you oxidize it using chromic acid, you form this cool compound, which is called benzoquinone, okay, or benzoquinone, and then you can oxidize it even further. So yeah, anyhow, I'm not really worried about the hydroquinones. Again, I won't ask you this, but in case you're interested, it's in here. So I won't ask you about that. I'm not going to ask you about any of this. But what I am concerned with is section 12.13, because this is using all of the reactions that we covered in this class, okay, and applying them, right? So we don't want to just learn one reaction at a time. We want to be able to use them to build something important. Now, I'm not going to spend a lot of time on this section, on this slide, because every single reaction on here, they were all learned in Organic Chemistry 1. These were all covered in Chemistry 3101. We're not interested, or we are interested in these reactions, but we're not, they're old, okay? We learned them a long time ago. But in this chapter, we talked about how to oxidize a primary alcohol using PCC to an aldehyde. We also talked about if you take a primary alcohol and you treat it with chromic acid, H2CrO4, that forms a carboxylic acid. Just one thing I'll remind you of is you never just write H2CrO4. You always have to write out the reagents like chromium trioxide, aqueous acid, and acetone. Then we talked about the reduction of an aldehyde to an alcohol. So you could use lithium aluminum hydride. Your second step can be water, or it could be H3O+. These conditions, you could also use sodium borohydride. So sodium borohydride and methanol, ethanol, or water. I'll just put methanol, okay? We said oxidation of a secondary alcohol. So again, this is primary. Oxidation of a secondary alcohol, well, it doesn't matter what you oxidize it with, you always get a ketone. And again, we talked about reducing that. So nothing really new there. So now we know how to do all these different conversions between alkenes, alkynes, alcohols, alkyl halides, ketones, aldehydes, etc. And I think I went over this slide with you last class, and the only part that we hadn't covered last class was the section on oxidation. So now that we've covered that, you know all of the reactions on here, plus a lot more. So you can see that we're going to build on our reactions and thus our synthetic strategies over the course of organic chemistry too. Of course, if you want to make a carbon-carbon bond, you learn a new way to do that in organic chemistry too, and that is to use a Grignard reagent. If you have a ketone or an aldehyde, so ketone or aldehyde, you use your Grignard reagent. Okay, it's a good nucleophile followed by treatment with water or aqueous acid. Okay, so or aqueous acid, either one is acceptable. And then if you have an ester, so when we have an ester, we actually have to use excess of our Grignard reagent followed by water or aqueous acid. So you need a whole lot of your Grignard reagent in that case. All right. And then, synthesis strategies with multiple steps. Well, now that you know a new way to make carbon-carbon bonds, it really opens things up. So you have to be very, very solid on your synthesis in order to figure out these kinds of problems, right? Let's say you have something like this aldehyde here, which has 1, 2, 3 carbons, but then we want to make a ketone. Well, in that case, you'd have to use a Grignard, right? Because we know that a Grignard is a good nucleophile, right? But when it attacks, and after you do a proton transfer, you form an alcohol. So then you'd have to oxidize it using your chromic acid in order to produce the ketone in that case. So with that in mind, what I'd like to do is I know we haven't gone that far. I guess we've been on for about 45 minutes. I'd like to take a short break and give you all a chance to try 12.24. So I want everybody to get a piece of paper out. I want you to try these ones, and I want you to try, so let me double check something here. So I want you to try 12.24 and 12.26. Okay, so 12.24, and then I want you to try 12.26. Okay, just those two. And then after that, I want to go over even more synthesis problems with you if we have time. Okay, so again, we're going to take a short break, and then we're going to come back and try all these. So if you're watching the videos, it's a really good opportunity to try them, and then you can open up the next video and go over the solutions with us.